So, can you see my screen?
Yes, go ahead.
Okay. Hello, everyone. Let me introduce myself. My name is Muhammad Zaki Almuzakki, and in Indonesia, you don't usually call people by their first name. So
I'm sorry, I broke
it's
the
fine.
law.
It's fine.
But
People
by
usually
which
call
name
me
do you call people?
the middle name, Zaki.
Middle name, Zaki. Okay.
Yeah. So today I'll talk about the paper titled Port-Hamiltonian Neural Networks for Learning Explicit Time-Dependent Dynamical Systems by Desai and his colleague. So in this talk, it's basically what we are going to learn here is that they are trying to propose a new method, but not really, not much analytical explanation in the paper. But anyway, so the motivation is that, okay, so this is the outline of my talk today. And the motivation of this work is that first, well, now it is well known that neural networks is considered as a universal function approximators. So in this case, if we talk about dynamical systems, differential equations, and basically we can learn the long-term behavior of that dynamical systems by using neural networks. It's some setups, and in this case, what we need is that we need to have the state data, and we need to add to the neural network is that we assume that the data obeys a certain physical laws. And this field of study is called scientific machine learning. And the problem is that most research in this field, they focus on autonomous systems. So basically, you don't have any external force. And most of the time, when we talk about physics, they only try to learn a system that conserve energy. But in this case, the authors, they want to deal with systems that contains maybe you'll have external force, maybe you'll have energy dissipation, and so on. So in this case, they used a rather well-known framework called Port-Hamiltonian framework, which most people know, most people in physics and in engineering knows Hamiltonian. And Port-Hamiltonian framework is basically you have Hamiltonian systems. We introduce energy dissipating elements and external force there. Then we have Port-Hamiltonian frameworks.
But Zaki, if you have external force, it can still be a Hamiltonian system. So if you have a conservative, conservative external force, you can express this as a gradient of the potential.
For sure.
Do they mean here non-conservative, the one that cannot be expressed? Okay, that's different.
But in Hamiltonian system, you don't. I think it's not possible to add to add the dissipating elements there.
That's for sure. You don't have it. Yeah, dissipation is of course non-Hamiltonian.
Yeah. So we have this in Port-Hamiltonian framework, but we'll come to that later.
Yeah, let me just defend a little bit physicists as well. Even if you do not have a dissipation in a Hamiltonian system, you can consider an enlarged system which is Hamiltonian, and then once you coarse grain over some part of it, then what's left may be considered as a Hamiltonian system with dissipation. So you can, the bigger system is still Hamiltonian, but the smaller one that you analyze but I understand what you're saying. Thank you.
Yeah. So what I like about the Port-Hamiltonian framework is that, for example, if you have a big system that is Hamiltonian, you can break down the system into smaller parts that they're essentially they contains ports that connects one parts to each other, and in this case there is a good chance that each small systems, they have their own energy dissipating elements, and we can treat this force, external force, as the port connecting one small part to the other. So this is basically the Hamiltonian system. And what is actually Hamiltonian neural networks? So in this case, there's a paper by Greidanus. They want to try to solve the ideal mass spring system, but through neural networks. So they train, they generate some training data sets from the system by using numerical integrator, and then they train them in a way that in the end they will have the predicted states match almost exactly as the original as the ground truth. So in this field, people know more about PIN, or physics informed neural networks, which they use in here, basically the baseline neural networks. So basically in this baseline neural networks, what people do is that they have the states as the input, and then they directly predict the time derivative of the states. But in the Hamiltonian neural networks, instead of directly predicting the time derivative of the states, what they predict is the Hamiltonian, is the total energy of the system, and then from that total energy, they try to recover the time derivative of the states using the differential equations. So that's what they do basically, and you can see in this paper they've shown that with the baseline neural networks, the states either grows or shrink, which should not happen in the Hamiltonian system. But by introducing by predicting the Hamiltonian instead of directly predicting the states, the time derivative of the states, we can still get conservation there. So that is the idea of Hamiltonian neural networks. Then after this, we will learn a little bit about the concept of Port-Hamiltonian. So basically, what is a Port-Hamiltonian framework? You can see on the left side. On the left side here, this is basically the general nonlinear Port-Hamiltonian systems. It's input, state, output Port-Hamiltonian systems, where we have J as the interconnection matrix. In the Hamiltonian systems, you see there is a matrix as this matrix is basically the interconnection matrix that interconnect the Q here is the position vector, and P is the momentum. This matrix is basically interconnecting the position and the momentum. And in the Port-Hamiltonian framework, we have the matrix J as the interconnection. So if we take J as 0, 1, minus 1, 0, and R 0, G 0. We recover the classical Hamiltonian systems. And in this case, in Port-Hamiltonian framework, we have the damping coefficient or the damping matrix. That is the matrix R, which is symmetric and positive definite. And then we have, of course, we have the total energy or the Hamiltonian. And U and Y, they are the ports, the external ports. So U being the input port and Y is the output ports. You can see the abstraction on the right side, where this is a single port Hamiltonian system, where you have the storage element. You can think of the storage element as a spring. For example, a spring is basically the storage element. So you don't the energy does not dissipate in this case. And you have the dissipation element, and you have the external ports. And you see the symbol E and F here is basically E stands for effort and F stands for flow. So if you have effort such as force, you will get flow from the system. If typically, if we have force as the effort or the input ports, we have the natural output ports or the flow ports would be the momentum in this case.
Zaki, can I ask you a question? So your J depends on X, although the symplectic matrix doesn't.
This is the general nonlinear Port-Hamiltonian system.
Right. So it depends on X. It's already not Hamiltonian, right? If J depends on X. Because usually in symplectic form, it doesn't depend on X, right? It's so it is so even if we set R and G to 0. The fact that J depends on X already something.
No. In this case, J can depend on X. It can also be just constant matrix.
Right. Now I'm saying that if it does depend on X, then it's no longer Hamiltonian. It's already what you would call Port-Hamiltonian.
Yeah.
Mm-hmm.
So so that's basically the Port-Hamiltonian framework, and what is being considered in this paper is basically a simplified version of general Port-Hamiltonian systems. That is the system on the left, with again the state being position and momentum, and we have the interconnection J 0, 1, minus 1, 0. And we have the constant damping coefficient 0, 0. So we only have N here in the bottom right corner. With N must be positive because in the Port-Hamiltonian setting, the matrix R should be positive semi-definite. And they also use the lumped time dependent external force vector. G times U being the this vector, so 0 and some force, some time dependent force, and we don't consider the output port here in this case. So we just take the X dot, and basically that's it. So what is proposed by the authors here is the picture E. So we have the standard or the baseline neuronal networks. It basically the first to the top one, what are being predicted they directly predict the time derivative of position and momentum. But the difference is that in the baseline neural network that is used in the experimental setup later is that they also they use they add time as one of the input. So not only the position and momentum data, but also the time. And picture C is the standard Hamiltonian neural networks. So basically, we have position and momentum as the input, and we predict the total energy or the Hamiltonian. And from that, in the numerical setting, we can use autograd, for example, to obtain Q dot and P dot. And I think few months after the Hamiltonian neural networks paper were published, some other groups, they also present, they try to add, they try to generalize the Hamiltonian neural network by introducing the time as the input. The C and D, they are basically the same. The difference is that in image D, you have extra inputs that is time. And in the Port-Hamiltonian neural network setting, first we have the Hamiltonian neural network here. And then the force, time-dependent force, is predicted in different subsystems directly from the time. And then the dissipation, the damping coefficient is predicted also differently. And then the predicted position, time derivative of the position and momentum is obtained using this relation. And in this paper, they use this loss function on the left. So basically the L2 norm on the on Q dot and P dot. But the interesting thing is that they use different norm on the predicted force and damping coefficient. In this case, they claim that after their experiments, there are many experiments using L1 norm instead of L2 norm for the force and damping coefficient. The Port-Hamiltonian neural network works much better than the other norms. And in the experimental setup, we have also here the regularization parameters lambda f and lambda n. The authors, they use grid search to find the best performing parameters. So I personally feel they're cheating a little bit in this case.
So Zaki, can I ask? So they are not now training for the Hamiltonian or like whatever Port-Hamiltonian. They're training again for the ground truth, right?
Yeah.
Okay. So have they tried to do it?
I haven't tried it myself. But
have they tried to train it for, because there's an expression for, for a Hamiltonian, there's expression for your J matrix. You can try to train directly for those things, for H, J, whatever, F, force.
Yeah. Yes.
But they haven't done that. That would be like extrapolation of the pin to the Port-Hamiltonian system, I guess.
Yeah. So after this, some of the experiments that they did, and the setup is like this. So the grounded truth data are generated using Runge-Kutta fourth order integrator with very small time steps. And they in this case they want to ensure the relative tolerance to be almost negligible in this case, and the performance are assessed using mean squared error, where they assess the state mean square error and the energy mean square error between the ground truth data and the Hamiltonian. And the first experiment is a very simple mass spring system. So basically, it's classical Hamiltonian systems where no force, no damping, and of course, in this case, the Hamiltonian neural network works much better than the rest. Port-Hamiltonian neural networks works a little bit worse. Why? Because in the Port-Hamiltonian neural network setting, they also try to predict the force and damping, which in this case should be 0. But as you see, the order are very small, so they are still quite nice in this case. And then they add damping, but no external force. As you see here, when there's damping, of course, Hamiltonian neural network, since you cannot add damping there, it works much worse than Port-Hamiltonian neural networks in this case. So you can recover the damping here almost exactly, but you still have the force. And then in the next setting, we have forced mass spring system, but no damping. Port-Hamiltonian neural network in this case still works, still outperform the rest of the methods. You see here the recovered force almost the same as the ground truth force. I think in this case they used this is just simple negative sinusoidal waves for the external force, but I believe that when they have they also learn the damping here, which should be 0, but then I guess that the damping is actually if we add the damping to the external force, the predicted total force and the damping element should be much closer than the ground truth in this case. And they also try to experiment on the Duffing equations. I'm not that familiar with this equation, but what they try to show here is that, okay, again, the bottom figure shows that Port-Hamiltonian neural network still outperform the other approach. But if we see closely on the Hamiltonian, on the level set of the Hamiltonian plotted on the phase plane like this, we see that the Port-Hamiltonian neural network is clearly much closer than to the ground truth data than compared to the Hamiltonian neural network or the time-dependent Hamiltonian neural networks, because I think in this case, in the standard Hamiltonian neural network, and the time-dependent Hamiltonian neural networks, the system they begin to learn somehow distorted Hamiltonian in this case. So yeah, this is what happened. So from this, they have also an extra experimental results where they want to show that in the chaotic setting, which I believe that it is still there are still many problems with larger class of physics informed neural networks for this for chaotic system. In the chaotic system, here basically the Port-Hamiltonian and baseline works better than the standard Hamiltonian and time-dependent Hamiltonian neural networks. So they only show for the chaotic setting, they only compare the baseline and the Port-Hamiltonian with the ground truth. They plot the Poincare section of the chaotic Duffing oscillator, and we see here that in the Port-Hamiltonian case, we can recover most of the ground truth data. And that is basically what I learned about this paper. So yeah.
Thanks. There are a couple of questions. So Wahid, you wanted to say something about the broad theorem. Go ahead.
Yeah, thank you. Yeah, I made a comment about the Darboux theorem. I mean, the J term is, if it's a symplectic form, you can transform it I mean, you can change the coordinate system on the phase space, and again, you can make it coordinate independent. I mean, this is the definition of the canonical coordinates.
Right, but for that you need to make sure that you can kind of bring this J to the other side. You can invert it, right? So you want to decompose J in something that depends on the symplectic form without X dependence, and then something that depends on X, and then you can like apply inverse on both sides, and then kind of move this X dependence to the left and redefine X. But you know, if you just write it a generic form, I mean, it doesn't necessarily imply you that you can get rid of it so easily. Unless it's, as I said, decomposable and then invertible.
Yeah. I said with the assumption that this is a symplectic form. I mean, if
it's symplectic form, that's by definition is already has an If it is symplectic form, then I completely agree with you. There is nothing.
Yeah, I didn't read this paper, but I think that they assume that the J part is symplectic form.
If it is, then by definition that's what it is. Yeah. Perfect.
There was another part which wasn't symplectic, and there was another part which was U dependent on. Yeah.
That's right. Yeah, those other parts, of course, change everything. Yeah. Good. Thanks.
Yeah, I meant if only there is J part here, we can always make the transformation and go back to. I mean, obviously this is a Hamiltonian system, and we can make a transformation and go over the canonical coordinates. With the, I mean, okay, H is going to change, but okay.
But I think you agree, right? So if you cannot like invert J, bring it to the other side, and change it.
I agree.
Then it's not a Hamiltonian and so on. But if it is Hamiltonian, of course, whatever form you write it in, we know what it is. Okay, perfect. Thanks. We're in agreement. Good. Okay, and there is Vladimir, your comment. Go ahead. Or question. That was a question.
Yeah, for the figure where you had all the architectures, I was just confused. And like in the paper also didn't really see them explain like what is exactly are you training the N hat theta 3 for the Port-Hamiltonian? Like is that trained on time, or like it's in like its own separate box?
No, well, I was asking this question myself when I read this paper, actually, but this is the N hat theta 3 is not time dependent in this case, so they just independently predicted. I don't know how they.
It's like basically a fixed bias.
Yeah. Oh yeah. That's correct. That's precisely
Oh, okay. Yeah, I was thinking like this is like some okay. This is like simple. Okay, thanks.
Okay, and we have one more question from George. So if you can articulate it.
Yeah, sure. So I know that some people are using machine learning to predict analytical equations. Specifically, I know at MIT and some other places. For example, they'll take the state of the system, a bunch of data regarding how it moves around, and they'll predict the Hamiltonian for that system or some other various equations.
That's
Can
exactly
the
what Zaki called Hamiltonian neural networks. That's exactly it.
Okay, cool. And
Oh,
so
yeah.
can the analytical Hamiltonian be extracted from this, or
Well, from what I've learned so far, I haven't found any real work where they actually try to recover the equation itself.
Okay.
What they do is just purely numerical.
But hold on. Then I don't understand this. I thought there was whole idea. First, you can do the brute force, just train for the ground truth. That didn't perform well. The second type, what George mentioned, is that people who say, okay, well, we know the system is Hamiltonian, so let's train for Hamiltonian and find it. And that's
but what you learn is not this. Okay.
You
You
learn
assume that the
Hamiltonian.
system, you assume that the system obey Hamiltonian or Port-Hamiltonian or whatever, but they just use that as a what I believe as a bridge to find the dynamic data, just the numerical data, not the
Analytical
equation.
expression.
So, yeah.
But hold on, then I don't understand, right? In the very beginning, you drew this new neural network where you had P and Q inputted. What output was H of P and Q. Then you take this H of P and Q, you differentiate it, and you get what Q dot and P dot should be. And that's what they would call the Hamiltonian neural network. So you are numerically reconstructing the function, which is H of P and Q.
Yeah.
Okay, so now whether it has a nice analytic expression, that's separate, right? So you may be an ugly function that has no analytics, and then you have to restrict yourself. I'm looking at certain type of functions, and then maybe I will be able to uncover what the analytical form of it. But they do exactly that in the H and N. Now in the Port-Hamiltonian, I didn't see that happening, because I would argue that if you have an expression, analytic expression of how your things change, whether it's Hamiltonian or beyond Hamiltonian, just try to train for the elements in there. For H, for J, for whatever you call, force, for dissipation, for everything. But they don't seem to do that. And then the next step would be exactly what George asked, can you have an analytic form for that? But that would come.
It's not there.
It's not there. It's not done. All right. I mean, we cannot expect them to do everything. Right, we have 2 more questions now.
No, it's not. It's not the question.
Symbolic regression. There we go. Now we're in a business. Yes. So now we have a good term. It is symbolic. Yeah. Exactly. All right. Other questions? I mean, I cannot read all the comments. If you have questions, just go ahead and ask. If there are no other questions, I will stop recording. Thank you. That was fun.
Thank you.